Most of the time, it feels natural to think of ourselves as separate from the universe. We live down here, on a small, familiar world. And the cosmos lives up there, far away, something we look at, something we study, something we admire from a safe distance. The stars seem like distant decorations. The moon is a light in the night. The planets are wandering points. And we, in comparison, feel local, contained, made of ordinary matter that belongs to Earth alone. In the quiet rhythm of an everyday moment, that illusion becomes even more comfortable. You breathe in without effort. Air moves through your lungs. Your chest rises and falls. You touch a table, a blanket, a cup warmed by your hands. You stand on solid ground and trust it. Nothing about these small experiences suggests any connection to nuclear furnaces or ancient galaxies. Intuition tells us there's a clean boundary, the human body below, the cold universe above, unrelated realms. And then comes the first scientific surprise, gentle but unsettling in its implications. Modern astronomy didn't just map the stars, it learned what they are made of. By splitting starlight into its hidden colors, scientists discovered signatures of specific elements, cosmic fingerprints, stamped into light itself. And from that, a deeper story emerged. The elements in your body are not merely from Earth. They were forged in stars. This is stellar nucleosynthesis, the slow, patient creation of heavier elements inside stellar cores. In a star's deep interior, pressure and heat are so immense that atoms collide and fuse, building new atoms from old ones. Hydrogen becomes helium. Helium can become carbon. And in the long lives of stars, layer by layer, an invisible chemistry unfolds, quietly constructing the ingredients of complexity. So the calcium that gives your bones their strength, the iron that lets your blood carry oxygen, the carbon that forms the backbone of your DNA, these were not born with Earth. They were once inside ancient suns, held in their glowing interiors, as if waiting for a future they could never imagine. And that leads us into an even wider view, the universe as a chemical story. In the beginning, the cosmos was simpler than the world you know. After the early fireball cooled, there was mostly hydrogen and helium, with only tiny traces of anything else. No iron, no calcium, no carbon-rich molecules drifting through space. The early universe had the rawest possible palette. It took massive stars, short-lived, heavy, and intense, to change that. These giants built mu elements in their cores, and when they died, they did not fade quietly. They exploded, supernovae, violent, brilliant endings that scattered newly forged atoms outward, seeding space with the materials of future worlds. In that sense, nearly every atom heavier than helium carries a stellar origin story, written in heat, gravity, and time. And once released, those atoms began a journey hidden in every cell of your body. For billions of years, particles drifted through interstellar darkness, mixed into dust clouds, folded into new stars, and thrown out again. Some of the atoms inside you may have wandered through ancient galaxies, passed through multiple generations of suns, and traveled unimaginable distances before ever becoming part of anything that could breathe. The mystery isn't just that these atoms exist, it's how they found their way into living organisms, arranged into tissues, thoughts, and quiet awareness. So here is the disturbing question, simple enough to whisper, and heavy enough to echo. How did the debris of exploding stars slowly transform into the atoms inside your body? In this quiet journey together, we'll follow that trail, through the element-making violence of supernova nucleosynthesis, into drifting interstellar dust clouds, onward to planetary formation, atmospheric chemistry, and the looping biological cycles that keep atoms moving through life. And if you enjoy calm voyages through cosmic mystery, you're warmly invited to like and subscribe, and stay with us as the story deepens. Because once you truly absorb it, it lands like a soft intellectual shock. You are not merely in the universe, observing it from afar. You are made of it. The boundary between life and cosmos may be thinner than we ever imagined. The atoms inside you were already traveling through space billions of years before Earth existed. But to understand how those atoms reached you, we must travel back to the violent birthplace of the elements themselves. In that young universe, everything was simpler and emptier, and yet filled with possibility. There were no planets, no oceans, no bones, no breath. There was mostly hydrogen, the lightest atom, and helium close behind it. A vast, thin mist stretching across darkness that had only recently cooled enough for atoms to settle into existence. For a long while, that mist did not glow. It drifted, almost featureless, as gravity quietly began its patient work. Gravity doesn't rush, it persuades. Wherever the gas was slightly denser, wherever a region held just a little more matter than its surroundings, gravity pulled a little harder. Over time, those small differences grew. Clouds formed, then larger clouds, immense reservoirs of hydrogen, so wide they could have swallowed whole galaxies that would come later. Within them, the gas began to gather into knots, slowly at first, then faster, as the pull intensified. As the cloud contracted, it warmed, not because anything was burning, not yet, but because squeezing matter raises its temperature. Particles fell inward, accelerating, colliding, jostling, turning motion into heat. The center grew denser and denser, until it became something like a seed, a protostar, wrapped in a cocoon of infalling gas. And then, in the deepest heart of that gathering sphere, pressure climbed to an unimaginable level. Hydrogen nuclei, single protons, were forced so close together that the rules of ordinary matter began to blur. At those temperatures and densities, even the natural repulsion between positively charged protons could sometimes be overcome. When two protons met under the right conditions, they could fuse. That first fusion was a quiet turning point for the universe. In the core, hydrogen began to combine into helium. A tiny amount of mass vanished in the process, transformed into energy, released as light and heat. The protostar became a star, one of the first lights to ever shine. It was not a gentle candle. These earliest stars were often enormous, far more massive than our sun, burning bright and fast, living short, intense lives. They were born in a cosmos that had never seen starlight before, and their radiance began to sculpt the darkness. This is where the story of the elements truly begins. Because a star is not only a light in the sky, a star is a furnace, a cosmic engine, a pressure cooker made by gravity. It takes the simplest ingredients, and in its core, begins to rewrite them. Inside a star, the universe learns chemistry in a new way, through heat, through compression, through time. As hydrogen fuses into helium, energy pushes outward, fighting gravity's inward pull. A star becomes a balance, gravity trying to collapse it, fusion trying to expand it. That balance can last millions, sometimes billions of years, depending on the star's mass. And during that long equilibrium, something profound is happening. Something that will one day make rocks, oceans, and living cells possible. Fusion is a kind of alchemy, but it is real. In the searing core, lighter nuclei join together to form heavier ones. Each step requires immense temperature and pressure, like climbing a ladder where every rung is harder to reach than the last. The star spends most of its life converting hydrogen into helium. But when the hydrogen in the core begins to run low, gravity gains the upper hand for a moment. The core contracts, heating further, until a new kind of fusion can begin. Helium starts to fuse. 3 helium nuclei can combine in a sequence to form carbon. This is the triple alpha process, and it is one of the universe's most important tricks. Carbon, so central to life, to complex molecules, to the very idea of biology, can be made in the deep interior of stars, not as an afterthought, but as a natural consequence of physics. And once carbon exists, the furnace has new fuel. In massive stars, the temperatures rise high enough for carbon to fuse into heavier elements. Carbon can combine to form neon, sodium, magnesium. Then oxygen becomes abundant, and oxygen can fuse too, creating silicon, sulfur, and more. Step by step, a massive star manufactures a growing library of elements. This is stellar nucleosynthesis, the forging of new atoms in stellar cores. It's easy to imagine a star as a simple ball of fire, but inside, it becomes structured, layered, like a living geology made of plasma. The most massive stars develop an onion interior. In the center, the core holds the heaviest element the star can currently fuse. Around that core is a shell where a slightly lighter element fuses. Around that, another shell and another, each one a different burning stage. Hydrogen may still be fusing in an outer shell long after the core has moved on to helium. Helium may burn in a shell while carbon burns deeper in. Farther in still, oxygen burns, then silicon. Each shell is a zone of intense reactions, each with its own temperature, its own timescale, its own kind of light. Though none of that light escapes directly. The star's surface glow is only the final softened expression of violence happening far below. In the late life of a truly massive star, the layering becomes extreme. The core is dense and blisteringly hot. Above it, shells of silicon, oxygen, neon, carbon, helium, hydrogen, stacked like cosmic strata. It is a star that has become a factory, assembling matter into more complex forms, pushing toward a boundary it cannot cross, because there is a limit to what fusion can do. Fusion releases energy when it combines light elements into heavier ones, but only up to a point. Up to a certain element, each fusion step produces a nucleus that is more tightly bound than the last, and that extra binding energy is what gets released as heat and light. That is what keeps the star shining. That is what holds gravity at bay. But as the star climbs the periodic table, it approaches a peak, a turning point, a cliff edge hidden in the physics of atomic nuclei. That turning point is iron. Iron is unusually stable. Its nucleus is so tightly bound that fusing iron into something heavier does not release energy. It costs energy. It is like trying to roll a boulder uphill instead of letting it tumble down. Past iron, fusion becomes an energy drain, not an energy source. So when a massive star finally builds an iron core, it has reached a dead end. For a time, the star can still survive by fusing silicon into iron in a shell around the core, adding more iron ash to the center. But the iron core itself cannot provide the outward pressure that fusion once supplied. It sits there, growing heavier, growing denser, supported only by quantum rules, by the pressure of electrons packed so tightly they resist being squeezed further. Yet even that resistance has limits. As the iron core gains mass, gravity presses harder. Photons in the core become so energetic that they begin to tear apart heavy nuclei, breaking iron into lighter pieces, an act that consumes energy, stealing heat from the core. At the same time, electrons are forced into protons, creating neutrons and neutrinos. This process, called electron capture, removes the very particles that were providing pressure. The core loses its support from within. And then, in a moment that is both sudden and inevitable, collapse begins. Not a gentle sinking, not a slow settling, a free fall. The iron core plunges inward at a significant fraction of the speed of light. In less than a second, a region larger than Earth can crush down to a sphere only tens of kilometers across. Matter becomes so dense that atoms themselves are flattened. Electrons and protons merge into neutrons. The core becomes something like a giant atomic nucleus, a newborn neutron star forming in the center of catastrophe. And as the core collapses, the outer layers, those onion shells of burning elements, are still falling inward too, pulled by gravity, unaware that the heart of the star is failing. Then the collapse hits a wall. At nuclear densities, the strong force and neutron degeneracy pressure push back. The core stiffens abruptly, and the infalling material slams into it. A shockwave forms, an outward-moving ripple of violence. For a moment it stalls, fighting against the weight of the star above it. But the physics of the collapsing core is not finished. Neutrinos, those ghostly particles produced in enormous numbers during the collapse, stream outward, carrying away energy, and also, in a crucial way, depositing energy into the surrounding layers. The shockwave is revived, and the star explodes. A supernova is not simply a bright flash, it is a transformation of matter on a grand scale. For a few weeks, a single dying star can outshine an entire galaxy. It can be visible across intergalactic distances. But the brightness is only the surface story. The true drama is in the temperatures and pressures that exist for an instant as the shockwave races outward. For a brief incandescent moment, the environment becomes hotter than billions of degrees. In that furnace, far hotter than the steady burning core ever was, new nuclear reactions ignite. It is here, in the violence of the explosion, that many of the elements heavier than iron are formed. Because while steady fusion cannot climb past iron without losing energy, the chaos of a supernova can force matter over that barrier. Neutrons flood through the exploding layers. Nuclei capture neutrons rapidly, faster than they can decay, building heavier and heavier isotopes in a chain reaction called the rapid neutron capture process, the R process. In these fractions of a second, the periodic table is extended. Gold, platinum, iodine, uranium, and countless other heavy nuclei can be assembled in the storm. Not all heavy elements come from supernovae alone. Some are also born in the mergers of neutron stars, in collisions so extreme they warp space itself. But supernovae are among the great distributors and forgers, seeding galaxies with rich chemistry, turning a universe once dominated by hydrogen into one capable of complexity. And among the products of these stellar deaths are the elements that life will someday borrow. Oxygen, abundant in the universe, essential to the air you breathe and the water that fills your cells, is forged in massive stars during their burning stages and then scattered outward when those stars die. Nitrogen, so crucial to proteins and DNA, is produced through stellar processes and returned to space through stellar winds and explosive endings. Iron, carried in your blood helping transport oxygen through your body, has its origin in the final stages of massive stars and in the supernovae that end them. Calcium, woven into bones and teeth, giving structure to living forms, emerges from the nuclear reactions inside stars and during their violent deaths. It can feel strange to think of biology in the language of astrophysics, but the connection is intimate. The chemistry of your body is not separate from the chemistry of the cosmos. The same rules that govern nuclei in a star govern the atoms that form your cells. The oxygen in your lungs and the iron in your blood are not merely made of stardust in a poetic sense. They are literal products of stellar interiors and stellar explosions, matter that has been processed, refined, and transformed by stars that lived and died long before the sun was born. When you consider it slowly, it becomes almost impossibly elegant. A star takes hydrogen, the simplest atom, and through a sequence of burning phases, creates carbon, the backbone of organic molecules. It makes oxygen, which will one day pair with hydrogen to become water. It makes silicon, a foundation for rocky worlds. It makes iron, a key ingredient in planetary cores, in magnetospheres, in the shaping of habitable surfaces. And in its final breath, it scatters these ingredients outward, mixing them into the galaxy's vast reservoirs of gas and dust. The supernova does not keep what it has made. As the explosion expands, it hurls stellar material into interstellar space at thousands of kilometers per second. The ejected debris forms a supernova remnant, a growing bubble of hot, glowing gas threaded with magnetic fields. Within it are atoms newly forged and atoms long held in the star's interior, now released. Carbon grains, oxygen-rich compounds, iron atoms, calcium nuclei, each one launched into the dark between stars. The shock wave plows through the surrounding interstellar medium, compressing gas clouds as it goes. It can trigger new rounds of star formation, squeezing nearby regions until they collapse under their own gravity, beginning the cycle again. In this way, death becomes a kind of creation. A supernova is both an ending and a signal, an energetic message sent into the galaxy that says in the language of physics, here are new materials, here is pressure, here is motion, here is change. Over millions of years, the remnant cools and slows. Its contents mix with the larger galactic environment. The heavy elements disperse into molecular clouds, into diffuse gas, into the cold dust that drifts like smoke through spiral arms. The galaxy becomes enriched, generation after generation, as stars are born, burn, and return their processed matter to space. This is what it means to live in a mature universe. The earliest stars began with almost nothing but hydrogen and helium, but each stellar generation added complexity, sprinkling heavier atoms into the cosmic sea. The Milky Way, over billions of years, became a place where rocky planets could form because silicon, magnesium, iron, and oxygen became common enough to build them. It became a place where water could pool on surfaces because oxygen was abundant enough to bind with hydrogen in great quantities. It became a place where chemistry could grow intricate because carbon, nitrogen, phosphorus, sulfur, and more were available to assemble the elaborate molecules that life uses. Galaxies, in a sense, learn over time. They start simple, and through the repeated lives and deaths of stars, they accumulate the ingredients for complexity. The universe recycles itself, slowly but relentlessly. What was once a thin primordial fog becomes a rich, dusty, element-filled medium, capable of making planets, and eventually, capable of making new. So when you imagine those ancient giants, those massive stars with layered hearts, try to picture not just their light, but their contribution. Picture them as crucibles, as furnaces so hot they alter the identity of matter. Picture their final explosion not as destruction alone, but as distribution, as seeding, as a grand exhale into the galaxy. Because the elements of life were not placed gently into space. They were thrown, cast outward in expanding shells, riding shockwaves, mixing into cold clouds, drifting through spiral arms. In that long quiet after the blast, the story becomes slower again. The fireworks fade. The remnant thins. The atoms continue on, carried by turbulence and gravity, by the subtle currents of the Milky Way. But once these elements are scattered into space, their journey has only just begun. Out there, beyond the bright punctuation of stars, the debris from a stellar death does not stop moving. It keeps expanding, almost like a breath released into a cold room, spreading wider and wider, becoming thinner and quieter with every passing moment. In the first thousands of years after a supernova, the remnant is still dramatic. A glowing shell, shockwaves racing outward, magnetic fields tangled like invisible threads. But time in space has a different rhythm. Give it 1,000,000 years, 2,000,000, 10,000,000, and that once violet bubble becomes something else entirely. The energy that made it shine leaks away, radiated into the dark, in wavelengths our eyes can't see. The gas cools, slowly surrendering its heat to the vastness around it. As the remnant expands, it thins. Particles that were once crowded together are now separated by distances that feel impossible by earthly standards. The pressure drops. The collisions become less frequent. The whole cloud begins to relax, like ripples on a pond, settling back into still water. And in that long cooling, chemistry begins to quietly take over. At first, the atoms are stripped and ionized, too energetic to settle. But as the gas cools, electrons start to rejoin nuclei. Simple atoms return to stability. Then, in the gentler conditions, they begin to meet, and sometimes to stick. Not in a loud, sudden way, more like a careful, patient arrangement. Carbon atoms bond with oxygen. Silicon pairs with oxygen too, building the first hints of rocky minerals. Iron condenses into tiny metallic grains. In pockets where the temperature and density are just right, molecules form. Carbon monoxide, water vapor, ammonia. Small, simple shapes that will later become the raw vocabulary of much richer chemistry. And then there is dust. Interstellar dust is not the soft powder we imagine on a shelf. It's made of tiny solid grains, often smaller than smoke particles, formed from silicates and carbon-rich compounds, sometimes coated in thin icy layers in the coldest regions. Each grain is a miniature archive of cosmic history. Atoms forged in ancient stars, assembled into something slightly more complex than gas. These dust grains are important in a way that's almost hard to overstate. They are seeds. Not seeds in the biological sense, but seeds in the cosmic sense. Surfaces where atoms can land, meet, and react more easily than they can in open space. Dust gives the universe a place to build. And as the supernova remnant continues to expand and cool over millions of years, its material does something subtle and profound. It stops being a glowing monument to death and becomes quiet, usable matter again. A thin, drifting supply of elements and grains, ready to be folded back into the galaxy's next act. Now imagine what happens after the light fades. The remnant dissolves into the general interstellar medium, tenuous mixture of gas and dust between the stars. This is the quiet ocean of interstellar space, and it is quieter than almost anything the human mind is used to. In the best vacuum chambers on Earth, engineers work hard to remove nearly every stray molecule. But even those chambers are crowded compared to much of the space between stars. In many regions of the Milky Way, you might find only a few atoms in a cubic centimeter, sometimes less. A few lowly hydrogen atoms, a trace of helium, and a scattering of heavier elements, all drifting in a darkness that is not empty, but close enough that it feels like emptiness. In this ocean, motion is slow and strange. Atoms do not swim, they don't flow like air in a room, they drift, guided by gentle pressures, by faint magnetic fields, by shockwaves passing through from distant events. They can travel for ages without touching anything at all. Collisions, so common in our atmosphere that we never notice them, become rare encounters, separated by long stretches of solitude. A single atom might wander across a region of space for hundreds of thousands of years before it meets another atom closely enough to interact. A dust grain might glide for millions of years, turning slowly, absorbing a photon here, releasing a little heat there, collecting a thin layer of ice in a cold pocket, then losing it when it drifts into warmer surroundings. And distances become their own kind of time. A light year is not just a number. It's a reminder that even moving at enormous speeds, the galaxy is wide. An atom drifting at a few kilometers per second, fast by human standards, still needs tens of thousands of years to cross a single light year. To travel tens or hundreds of light years, it may need millions of years. And during that voyage, the sky above it changes in slow motion. Stars are born and die. Spiral arms rotate. Clouds gather and disperse. Cosmic travel is not an adventure of moments. It is a pilgrimage measured in epochs. And yet, through all that silence, the atoms persist. They do not tire. They do not forget. They simply continue, obeying the quiet rules of physics, waiting for conditions to change. Because even in interstellar space, even in the thinnest regions, there is one influence that never truly stops working: gravity. Gravity is not always dramatic. It doesn't need to pull hard to be faithful. Over long enough timescales, even the faintest tug can matter. In the galaxy, gravity comes from many sources at once. Stars pull on nearby gas. Dense regions of the interstellar medium create gentle wells that draw in more material. The overall mass of the Milky Way, its stars, its dark matter halo, its clouds, creates a broad gravitational landscape, like a slow slope that everything rolls along. Most of the time, gas and dust are stirred by other forces too: supernova shockwaves, stellar winds, the shearing motion of galactic rotation. But gravity is patient. It gathers what turbulence scatters. It remembers what explosions forget. Gradually, in places where the balance tips, where cooling allows gas to lose pressure, where a region becomes just a little denser than its surroundings, matter begins to collect. Not quickly, not all at once, but steadily. Hydrogen gas, especially in its molecular form, begins to concentrate. Dust grains drift into the same regions, helping the gas cool further by radiating heat away. The colder the gas becomes, the less it resists compression. The less it resists, the more gravity can deepen its hold. Over time, these gathering places become molecular clouds. They are among the strangest objects in the galaxy, immense, cold, and dark. Some stretch for dozens, even hundreds of light years. They can contain the mass of thousands or millions of suns. And yet, they are so cold, often just 10 to 20 degrees above absolute zero, that they barely glow at all in visible light. To ordinary eyes, they are shadows, ink blots against the stars. Inside these clouds, the universe becomes quiet in a new way. The gas is denser than the surrounding interstellar medium, but still far thinner than any vacuum we'd call air. And yet, compared to the near emptiness between stars, it is a crowded place. Collisions happen more often. Molecules survive. Dust grains can grow icy mantles. Chemistry becomes richer, more elaborate, more willing to experiment. These clouds are nurseries, not because they are gentle, but because they are prepared. Cold and heavy, they are the places where gravity can finally begin to do something bold. Star formation happens inside molecular clouds, not everywhere within them, but in their densest knots, regions where material clumps together, where a slight overdensity becomes a target for gravity's long attention. These knots can collapse, fragmenting into smaller cores, each one a potential future star. And this is where the drifting atoms, after millions of years of solitude, begin to find themselves in company again, gathered into a vast, cold congregation, waiting in the dark. Somewhere in the Milky Way, long before Earth existed, one such cloud carried within it a special mixture. Not special because it was rare. Many clouds contain similar ingredients, but special because of what it would become. A region within that molecular cloud began to change. Perhaps a nearby supernova shockwave passed through, compressing the gas. Perhaps the cloud's own internal motions brought streams of material together. However it began, the result was simple and irreversible. A portion of the cloud became dense enough that gravity could overcome internal pressure. And so it started to collapse. As it fell inward, it did not fall straight. The cloud had a tiny amount of rotation, just a faint spin inherited from the galaxy's broader motions and the countless interactions of gas streams over time. That small rotation mattered. As the region contracted, conservation of angular momentum made the spin speed up, the way an ice skater turns faster when drawing in their arms. The collapsing material flattened into a disk. This was the pre-solar nebula, a rotating, dusty, gaseous structure surrounding a growing central concentration of mass. It was not a clean disk, not perfectly smooth. It was turbulent, layered, full of eddies and waves and temperature gradients. Some regions were warm enough to vaporize certain minerals, others were cold enough for ices to survive. Dust grains drifted through it, like tiny boats caught in slow currents. And within this nebula, ancient stellar debris found a new role. The atoms forged in long-dead stars, carbon from one kind of stellar furnace, oxygen from another, iron from the final moments of massive stars, were now mixed together in one swirling environment. Dust grains that had condensed in supernova remnants and in the winds of aging giant stars were now part of the disk's solid inventory. Some of those grains may have been older than the sun itself by billions of years, surviving interstellar travel, surviving the formation of the cloud, surviving the collapse into the disk. It's a quiet thought, and a powerful one. Our solar system did not start from nothing. It inherited. It inherited atoms from earlier generations of stars. It inherited dust that had already lived other lives. It inherited the chemical decisions made by the galaxy long before the sun was even an idea. This is the meaning of cosmic ancestry. Not a metaphor, but a physical lineage written into every element heavier than hydrogen and helium. The Milky Way is an old storyteller, and it tells its story through matter. Because galaxies are not static collections of stars, they are recycling engines. Over billions of years, gas becomes stars. Stars shine, and in their cores they transform simple elements into heavier ones. Some stars gently release their outer layers as they age, filling space with carbon, nitrogen, oxygen, and dust. Other stars end violently, scattering iron and nickel and rare isotopes in shockwaves that can seed entire regions with new chemistry. Then that enriched material mixes back into the interstellar medium. It drifts, it cools, it gathers into clouds again, and the cycle repeats. This constant renewal is cosmic recycling, the ongoing exchange between birth and death, between light and dust, between fusion and chemistry. It is not perfectly efficient. Some matter gets locked away in long-lived stars for tens of billions of years. Some is blown out of galaxies in powerful winds. But enough remains, enough returns, that over time the galaxy changes its composition. This is galactic chemical evolution. In the early universe, there was almost nothing but hydrogen and helium. The first stars formed from that simple material, and when they died, they began the long enrichment of space. Each generation of stars added new elements to the mix, raising the metallicity of the galaxy. Astronomers' word for everything heavier than helium. By the time our solar system formed, the Milky Way had already been running this chemical program for billions of years. The atoms that would one day become oceans and bones and breath were not young. They were ancient travelers, refined through repeated cycles of stellar birth and stellar death. So when the pre-solar nebula spun into being, it was already seasoned with history. And then, within that rotating disk, another slow miracle began. Dust grains, those tiny seeds from interstellar space, started to assemble into worlds. At first, it was almost unimaginably subtle. A grain of silicate, a fraction of a micron wide, drifts close to another grain. They collide gently. Sometimes they bounce apart. Sometimes they stick, held by weak electromagnetic forces, by the faint cling of surface irregularities. In cold regions, thin icy coatings can make sticking easier, like cosmic frost acting as glue. Over time, more grains join. Clumps form, fluffy aggregates, porous and delicate at first, like soot gathered into a fragile web. These clumps settle toward the midplane of the disk, where gravity and drag concentrate solids into a thinner layer. There, collisions become more frequent. The clumps grow. Millimeter-sized becomes centimeter-sized. Centimeter becomes meter. And somewhere in this progression, the physics changes. Larger bodies feel drag differently. They begin to drift inward toward the forming sun. They begin to interact gravitationally with their neighbors, not just through tiny surface forces, but through mass. As the clumps become boulders, and boulders become kilometer-sized bodies, a new word becomes appropriate. Planetesimals. Planetesimals are the building blocks of planets, small worlds in the making. Some are rocky, formed inside the warmer regions of the disk, where ices cannot survive. Others are icy, forming farther out, where water, methane, and ammonia can freeze and add mass. They collide, merge, and sometimes shatter. A slow cascade of construction and destruction. The disk becomes a place of impacts, but not the sudden violence we imagine from movies. This is a long, grinding process, measured in millions of years. A collision might release tremendous energy, yes, but then there is quiet again, and the fragments continue to orbit, and gravity continues to work. Some planetesimals grow larger, simply because they are slightly larger to begin with. Their gravity gives them an advantage, pulling in nearby material, sweeping up smaller bodies. This is runaway growth, a gentle kind of domination. A few objects become embryos, protoplanets, big enough to shake the disk around them, to clear lanes, to stir up orbits. In the inner solar system, where temperatures are high, the materials available are mostly rock and metal, silicates, iron, nickel, aluminum, calcium. These were once atoms drifting in interstellar silence, then dust grains in a molecular cloud, then particles in a rotating nebula. Now they are becoming something solid and enduring. Rocky worlds begin as dust. It's a humbling lineage. The minerals in mountain ranges, the iron in Earth's core, the calcium that will one day become part of living bone. All of it traces back to the quiet assembly of grains in a disk of gas around a newborn star. And still, through all of this, time remains the main ingredient. Millions of years pass as collisions build planets, tens of millions as orbits settle. The early solar system is not a finished sculpture, but a workshop, hot, dynamic, filled with debris, with impacts, with gradual sorting. Some material falls into the growing sun, some is flung outward, some becomes trapped in asteroids and comets, preserving ancient chemistry, like fossils in deep freeze. And within the disk, the central region grows denser and hotter. As more and more gas and dust falls inward during the collapse, the core of the forming system compresses. Compression raises temperature. Temperature raises pressure. The protostar at the center, our future sun, begins to glow, at first from gravitational energy, not yet from fusion, a faint light in the nebula. Around it, the disk continues to rotate, continuing to build, continuing to collide and merge and settle. The ingredients for planets are moving into place, guided by gravity's long, steady hand. And if you listen closely to this story, you can feel how quietly inevitable it is, not predetermined in every detail. Chance and chaos still play their roles, but guided by rules that have been shaping matter since the first stars lit up the universe. Dust becomes clumps, clumps become stones, stones become planetesimals, planetesimals become worlds, all from material that once drifted alone between the stars. And somewhere in that slow, ancient construction, in one small corner of that swirling nebula, a star ignited that would one day warm a living planet. That star began as a quiet gathering. In the cold dark of interstellar space, a cloud of gas and dust drifted without shape or direction for ages beyond counting. But gravity is patient. It does not need urgency. It only needs time. And in one region of that cloud, a slight unevenness, a small excess of mass, became a gentle invitation for more matter to fall inward. At first, the collapse was almost delicate. Microscopic grains of silicate dust and flecks of carbon-rich material moved closer together, brushing past one another like slow snow in a windless night. Hydrogen and helium, the most abundant elements in the universe, followed the same quiet pull. As the cloud contracted, it began to rotate a little faster, not because anything pushed it, but because spinning tightens as it shrinks, the way an ice skater turns faster when drawing in their arms. The collapsing nebula warmed as it fell inward, not from flame, not from fire in the familiar sense, but from compression. Gravity squeezed the gas, and the gas resisted. Pressure rose, temperature rose. Deep in the thickening center, matter collected into a dense growing knot, a protostar. It was not yet the sun, not yet a stable star. It was a gathering place, a furnace being assembled. It glowed from heat alone, radiating in the infrared, wrapped in the dust that had once been spread thin across light years of space. Around it, the remaining material did not fall straight in. Rotation forced it into a flattened shape, a wide spinning plane like a cosmic record turning in silence. This was the beginning of a protoplanetary disk, the birthplace of worlds. In that disk, the young sun continued to gain mass. Gas streamed inward along magnetic fields and turbulent currents, feeding the center. The pressure in the core climbed higher and higher until atoms were packed so tightly that their natural repulsion could no longer keep them apart. Hydrogen nuclei, single protons, simple and ancient, were pushed into encounters that would have been impossible in colder, looser space. And then, ignition, not like a match, not like a spark, more like a threshold crossed. In the core, hydrogen began to fuse. Protons joined through a chain of reactions, becoming helium, releasing energy with every successful union. A fraction of mass became pure radiance, in accordance with the deep, strange accounting of the universe. E equals mc squared, the conversion of matter into light. This was the moment the sun truly became the sun. Fusion created an outward pressure, a steady push against gravity's inward pull. The star found balance, a long-lived equilibrium that would last billions of years. It began to shine in earnest, sending light outward into the surrounding disk, warming and shaping it. The solar wind, streams of charged particles, began to blow, clearing away some of the remaining gas, sculpting gaps and edges, and setting the stage for smaller bodies to assemble. And all the while, the protoplanetary disk continued to turn. Closer to the newborn sun, the heat was intense. Ices could not survive there. Water, methane, ammonia, frozen compounds that would remain solid in the outer regions, were vaporized in the inner disk. Only materials with high melting points could persist: silicates, metals, rocky minerals. Farther out, beyond what we call the frost line, colder temperatures allowed ices to remain. That single gradient, warm inner regions, cold outer regions, would shape the architecture of the solar system, determining what kinds of planets could form and where. Within the disk, dust grains began to collide.
At first, they stuck together through static charges and gentle adhesion, building clumps like fragile soot.
Those clumps collided again and again, gradually forming pebbles, then boulders, then bodies large enough for gravity to help them grow faster. Once a growing object had enough mass, it became a seed that pulled in more material. It swept its orbital path, gathering dust and rock and metal, increasing its gravity, accelerating its own growth. In time, the inner solar system became crowded with planetesimals, embryonic worlds, each one a small testament to the disk's ability to organize chaos into structure. Among them, one region of the disk began to produce something special. Here, at just the right distance from the sun, a body accumulated enough mass to begin the long process of becoming Earth. In the inner solar system, rocky materials were abundant. Silicate minerals dominated, mixed with metals like iron and nickel, and laced with traces of elements forged in older stars: magnesium, aluminum, calcium, sodium, phosphorus. Each collision brought new ingredients. Each orbit around the sun became part of a slow construction. But this was not a gentle era. The early solar system was violent, not out of malice, but out of physics. There were too many bodies sharing too little space, orbits crossed, gravity tugged, resonances built up. And so, impacts were inevitable. Worlds in progress struck one another with staggering energy, shattering and reassembling, melting and mixing. Earth's earliest form was likely a hot, growing sphere, repeatedly struck by objects that could be the size of mountains or the size of small planets. Every major collision dumped heat into the forming Earth, turning solid rock into magma, vaporizing surface material into temporary atmospheres, and driving differentiation, one of the most important transformations a planet can undergo. Differentiation is a kind of sorting. When Earth was young and partially molten, its materials were able to move. Dense substances sank, lighter substances rose. Iron, heavy and eager to gather, began to migrate inward, pulled by gravity through the molten interior. Nickel joined it. Together they formed the core, a deep reservoir of metal, hidden beneath thousands of kilometers of rock. Above the core, less dense silicate material remained, forming the mantle, still hot, still slowly flowing even today, moving at a pace too slow to notice in a lifetime, but fast enough to reshape continents over millions of years. And at the very top, the lightest portion cooled into a thin skin, the crust. This layered structure was not just a geologic detail, it was the making of a sanctuary. The core would generate a magnetic field, a protective bubble that would one day shield the surface from the sun's harsher winds and cosmic radiation. The mantle would drive volcanism and recycling, renewing the surface and releasing gases. The crust would become the stage where oceans could rest, where chemistry could persist, where life could gain a foothold. But before Earth could become calm enough for oceans and organisms, it had to survive its own beginning. In that era of collisions, there may have been a single impact so immense it reshaped Earth's destiny, a collision between the young Earth and a Mars-sized body, sometimes called Theia. The impact would have blasted molten rock into orbit, forming a glowing ring of debris around Earth. Over time, that debris gathered and cooled into the Moon, Earth's companion, its stabilizer, its quiet clock in the sky. Whether every detail of that event is exactly as imagined, the broader truth remains. Earth was forged through impact and fire, through repeated episodes of destruction that paradoxically built a more stable world. And as Earth cooled, the sorting continued. Iron and other heavy elements kept sinking, deepening the core. Lighter elements remained nearer the surface. Silicon, oxygen, aluminum, and calcium, elements that bond readily into minerals, formed the bulk of the mantle and crust. These compounds became the rocks that would one day be called basalt and granite, peridotite and sandstone, the raw textures of a planet. This is where we begin to see the ancient stellar story taking on a new form. Iron, so essential to blood and biology, sank into the deep earth, becoming part of the core's metallic heart.
It is strange, in a way, that the element we associate with strength and life-supporting oxygen transport spent most of Earth's history locked away in darkness, far below the surface, unreachable. Yet even that hidden iron serves you. It helps generate the magnetic field that guards the atmosphere and reduces the stripping of water and air into space. Above that iron heart, the crust accumulated lighter elements and compounds. Oxygen became abundant, bonded tightly to silicon to make silicate minerals. Carbon, far rarer than oxygen and silicon, still found its place, sometimes trapped in minerals, sometimes in the early atmosphere, sometimes delivered by meteorites, rich in organic precursors. Nitrogen, too, would become part of the air. Hydrogen, though light and easily lost to space, would become crucial once it found stable partnership with oxygen in water. And none of these elements were born here. Oxygen, the element that would someday fill your lungs, was forged in the hearts of massive stars and released in supernovae. Silicon, the backbone of rocks and the second most abundant element in Earth's crust, was produced in stellar furnaces near the end of a star's life, in layers where fusion built heavier and heavier nuclei. Iron, the endpoint of energy-yielding fusion, was made in the final catastrophic moments of dying stars, and scattered outward by explosions powerful enough to light up galaxies. Carbon, the element of life's architecture, was created in older stars through the triple alpha process, where helium nuclei combined in the intense heat and pressure of stellar interiors. Carbon drifted through space as dust, as gas, as part of complex molecules. It waited in clouds, it joined disks, it became rock, air, ocean, and eventually cells. So when we speak of Earth's crust, we are not just describing geology. We are describing a museum of stellar history, a surface made from ashes of long-dead suns. A thin, fragile layer where cosmic elements settled into patterns that could persist. But Earth was still not yet a comfortable home. For a long time, the surface was a shifting landscape of molten rock and cooling crust, repeatedly broken by impacts and reshaped by volcanism. The young sun shone with a more volatile temperament, sending bursts of radiation and charged particles outward. The solar system still contained debris, and Earth still endured bombardment, and yet slowly the planet began to hold onto something precious: an atmosphere. At first, any gases near the surface were easily lost. Earth's gravity was still gathering its strength, and the sun's early activity could strip away lighter molecules. But as Earth grew and cooled, and as its magnetic field strengthened, the planet became better at keeping what it released. Volcanoes became the planet's breath. Gases dissolved in molten rock rose toward the surface. When magma erupted, pressure dropped, and those gases escaped into the air.
This process, volcanic outgassing, built the early atmosphere molecule by molecule, eruption by eruption. The first atmosphere was likely dominated not by oxygen, but by water vapor, carbon dioxide, nitrogen, and smaller amounts of methane, ammonia, sulfur compounds, and other gases. It was thick, hazy, and chemically active. Carbon dioxide helped trap heat, keeping the surface warmer than it might otherwise have been under the young sun's slightly dimmer light. Nitrogen accumulated as an inert background gas, a stable presence that would later become the main component of the air you breathe. But perhaps the most important ingredient released was water. Water vapor poured from volcanoes and also arrived from space, delivered by water-rich asteroids and perhaps comets. Each impact a splash of chemistry from the outer solar system. In the early heat, water existed as vapor in the atmosphere, swirling above the cooling crust. As the planet's surface temperature dropped, a profound transition became possible. Condensation, clouds formed, rain began. Not a gentle rain at first, perhaps, but long, persistent downpours lasting thousands of years. Water collected in low basins, filling them, merging them, becoming seas. The first oceans were born, not as a sudden event, but as a gradual accumulation. Earth learning how to hold liquid on its surface. And with liquid water came a new kind of stability. Water is a remarkable solvent. It allows molecules to move, to meet, to react. It carries heat. It shapes rock through erosion and weathering. It makes coastlines and currents. It creates environments where chemistry can persist long enough to become complex. In the early oceans, the chemistry was rich. Minerals dissolved into the water. Hydrothermal vents formed where seawater seeped into hot rock, reacted, and returned to the ocean loaded with dissolved metals and reduced compounds. Lightning flashed through the atmosphere. Ultraviolet light from the young sun energized molecules at the surface. Impacts delivered new ingredients and stirred the planet's surface like a spoon in a cosmic cup. Earth was becoming a laboratory, not a sterile one, but a wild, planet-sized experiment. And in that experiment, simple molecules began to link into more complex ones. Carbon, in particular, began to show its strange talent. Carbon atoms can bond in many directions, making chains, rings, branching structures. In the right conditions, carbon becomes an architect. Combine it with hydrogen, oxygen, nitrogen, phosphorus, sulfur, and suddenly the periodic table becomes a language, capable of writing molecules that store information, capture energy, build membranes, and catalyze reactions. Prebiotic chemistry is the story of how non-living matter begins to behave in lifelike ways without crossing the full threshold into life. It is a story still being studied, still unfolding in laboratories and in theories, but the broad strokes are clear enough to feel the wonder of it. In the early Earth environment, simple molecules such as carbon dioxide, methane, nitrogen, and water could be transformed through energy from lightning, heat, ultraviolet radiation, and chemical gradients into organic compounds, amino acids, sugars, nuclear bases, fatty acids. Some of these molecules may have formed in the atmosphere and rained down into the oceans. Others may have formed near hydrothermal vents where natural energy gradients provided a steady driving force. Still others may have arrived already assembled in meteorites, tiny parcels of cosmic chemistry delivered to a waiting sea. Over time, these organic molecules could accumulate, concentrate, and begin to interact in networks. In shallow pools, evaporation could have increased concentrations, allowing reactions that would be unlikely in dilute water. On mineral surfaces, molecules could align and bond in new ways, guided by the structure of crystals and clays. Microscopic compartments could have acted like natural cells, creating local environments where chemistry could cycle and intensify. Step by step, complexity emerged, not as a sudden miracle, but as a gradual thickening of possibility. Molecules that could copy aspects of themselves, even imperfectly, would persist longer. Networks of reactions that reinforced one another would become more common. Structures that separated an inside from an outside, simple membranes made from fatty molecules, could create protected spaces where chemistry became more organized. And in all of it, cosmic carbon played its role. This carbon was not invented on Earth. It was inherited. It was forged in stars long before the sun existed, carried through dust clouds, mixed into the protoplanetary disk, incorporated into rocks and oceans, delivered by impacts, cycled by volcanoes. It became the backbone of molecules that could bend, fold, and encode. It is worth pausing here, just for a breath, to sense the scale of that journey. A carbon atom in your body may have formed in the core of a star that died before the sun was born. It drifted for millions of years in cold darkness. It entered the solar nebula. It became part of a planet. It dissolved into an ocean. It joined a molecule. It participated in reactions that were not yet alive, but were preparing the way. And then, at some point in this long continuum, Earth crossed a line. Life began. The earliest life was small beyond imagination, and yet monumental in consequence. Microbial, single-celled, simple in structure, but not simple in function. Even the most basic living cell is a masterpiece of chemistry. Membranes that maintain gradients, molecules that store information, catalysts that speed reactions, systems that harvest energy from the environment. These first organisms likely lived in places where energy and chemistry were abundant, near hydrothermal vents, in warm, shallow waters, perhaps beneath protective layers that shielded them from harsh ultraviolet radiation. They did not breathe oxygen, because free oxygen was not yet available in meaningful amounts. Instead, they used other chemical pathways, fermentation, sulfur metabolism, ion-based reactions, ways of extracting energy that fit the early Earth's conditions. And once life existed, the planet was no longer merely a stage. It became a participant. Because life does something extraordinary. It cycles atoms. It takes matter from the environment, rearranges it, and releases it again. It builds structures, breaks them down, and builds anew. It accelerates chemical transformations that would otherwise happen slowly. It creates feedback loops between the living and the non-living world. Early microbial communities began to influence the oceans and atmosphere. They consumed certain molecules and produced others. They altered the balance of carbon compounds in the water. They contributed to the formation of sediments. They changed the chemistry of minerals. They turned Earth into a world with metabolism, a planet where chemistry developed rhythms. In time, some microbes evolved the ability to use sunlight directly, capturing photons and using their energy to build organic molecules from carbon dioxide and water. This was photosynthesis in its early forms. And one version of it, oxygenic photosynthesis, would eventually release oxygen as a byproduct, transforming Earth's atmosphere over vast spans of time. But even before oxygen filled the air, life had already begun its quiet work, weaving stellar elements into living patterns. Carbon moved from dissolved ocean chemistry into cellular structures. Nitrogen became part of amino acids and nucleic bases. Phosphorus, delivered through minerals, became part of energy-carrying molecules and genetic backbones. Iron, though much of it lay hidden in the core, was available in the oceans in dissolved forms, participating in early metabolisms and later becoming essential in proteins that move electrons and manage energy. The biosphere, this thin film of life on rock and water, began to awaken, not as a sudden bloom, but as a spreading. Microbes colonized new environments. They formed mats and layers, communities that could trap sediments and build structures. They began to create local ecosystems, exchanging molecules, competing, cooperating, evolving. And with that, Earth's living chemistry truly began. From this point onward, atoms would not only drift and settle. They would circulate, they would be borrowed and returned, they would pass from rock to ocean to cell and back again. The ancient elements forged in stellar furnaces had found a new kind of journey, one that moved not only through space and geology, but through life itself. And yet, this is not where the story ends. Because once life begins to cycle matter, the atoms that make you possible do not stay in one place. They travel through food webs and air currents, through shells and bones, through forests and plankton, through blood and breath. But the journey of those ancient atoms did not end with the birth of life. They continued moving through the planet's living systems. Not as a single stream with a single destination, but as countless quiet loops, circles within circles, the atmosphere turning over, the oceans breathing, forests rising and falling with the seasons, and within all of it, atoms trading places so gently
that the exchange feels like stillness. If you could watch the air above Earth over a long stretch of time, you might expect it to be simple, a thin, invisible blanket, quietly resting on the world. But the atmosphere is not a resting thing. It is in constant circulation, stirred by sunlight, and shaped by the spinning planet beneath it. Warm air rises, cool air sinks, winds glide along pressure gradients. Storms roll their slow spirals across continents and seas. And within this moving air, oxygen and carbon drift like passengers on an endless voyage. Oxygen, in the air, is mostly found as O2, two oxygen atoms bound together, traveling as a pair. Carbon, in the air, is often traveling with oxygen as well, in the form of carbon dioxide, CO2, one carbon atom held between two oxygens, like a tiny linear spacecraft. These molecules are not rare, they are not exotic, they are everywhere. And yet their movement is one of the most important stories Earth has ever told. Carbon dioxide is released into the atmosphere in many ways. Volcanoes exhale it from deep geological reservoirs. Fires return it from wood and leaf back into the sky. Every animal, every insect, every hidden microbe in the soil releases it too, as a natural consequence of using energy. Even the oceans, which absorb immense amounts of carbon dioxide, also release it back when conditions shift, when water warms, when currents change, when the chemistry of the surface adjusts. Oxygen has its own story. It is reactive, restless, eager to bind. It is used up by fires, by rusting metals, by chemical reactions in rocks, and above all, by living things. Every time an organism breathes oxygen to extract energy from food, those oxygen atoms leave the atmosphere and enter a new phase of their journey. And then, by different pathways, oxygen returns again, sometimes quickly, sometimes after long detours through water, through stone, through the tissues of life. So the atmosphere is not just air, it is a shared reservoir, an active interface between sky and biology, a global mixing chamber where chemistry becomes life, and life reshapes chemistry. When oxygen leaves the air, it may dissolve into the ocean, feeding plankton and fish. It may move into soil, supporting the roots of plants and the vast communities of microbes that live in darkness beneath our feet. It may enter a lung, cross a membrane, bind to blood, and become part of a heartbeat. Carbon dioxide, meanwhile, drifts from breath to leaf, from ocean to cloud, from decay to wind. It is exchanged between the living world and the non-living world so continuously that the boundary between them begins to feel less like a wall and more like a door that never closes. And that is the quiet miracle of Earth. The atmosphere is not separate from life. It is part of life's circulation system. The chemistry of the sky is braided into the biology of the ground. Nowhere is this more clear than in the slow green work of photosynthesis. In the daylight, in forests and fields, in algae blooms and garden leaves, an ancient transaction takes place. It is simple in outline and almost impossible in its deeper elegance. A plant opens tiny pores on its leaves, stomata, so small you could not see them without magnification, yet so numerous that a single leaf becomes a landscape of gateways. Through these openings, carbon dioxide slips inside. It is just a gas molecule, a carbon atom and two oxygen atoms, drifting in from the air. But once it enters the leaf, it becomes part of a much larger choreography. Sunlight arrives as photons, each one a small packet of energy that has traveled across space from the sun's surface. 8 minutes earlier, it was born in a furnace of fusion. Now it lands on chlorophyll, the green pigment that plants use to catch light. Chlorophyll absorbs certain wavelengths, and in doing so, it excites electrons, lifting them to higher energy states, like winding a spring. That energy is not used to create warmth or light. It is used to create structure. The plant uses the captured sunlight to split water molecules, releasing oxygen as a byproduct. And it uses the energized electrons, along with hydrogen from water, to begin transforming carbon dioxide into something entirely different. Through a cycle of reactions, patient, step-by-step chemistry guided by enzymes, carbon dioxide is reshaped. Bonds are broken. New bonds form. Carbon atoms that were once free-floating in the air become stitched into chains and rings. Sugars appear, glucose, the foundational fuel of life's chemistry. From there, the plant can build almost anything it needs. Cellulose for sturdy walls, starches for storage, oils for seeds, proteins when nitrogen joins the story. A whole architecture of living matter, assembled from air and water and light.
And the carbon at the center of it all. That carbon is not from Earth originally, not in the deepest sense. Carbon is forged in stars. It is created when stellar cores become hot and dense enough to fuse helium into heavier elements. It is a product of ancient stellar evolution, a kind of cosmic craftsmanship that took place long before Earth had oceans, before it had continents, before it had an atmosphere to circulate at all. Those carbon atoms were scattered into space when stars died, some in gentle winds, some in violent explosions, and they drifted through the interstellar medium, joining clouds of dust and gas that would eventually become new solar systems. Some of that carbon became part of Earth, some became part of its rocks, some dissolved into its oceans, and some found its way into the air as carbon dioxide, waiting for life to learn how to catch it. So when a plant pulls carbon dioxide from the atmosphere, it is not just cleaning the air, it is collecting stardust. It is taking atoms that once belonged to ancient suns and locking them into a living form. Sunlight, born from fusion, powers the transformation, and the result is food, matter shaped into meaning. This is one of Earth's great alchemies, not mystical, not supernatural, but still astonishing. Air becomes leaf, light becomes sugar, cosmic carbon becomes a tree ring, a blade of grass, a grain of rice, a wildflower opening in morning sun. And then, because life is not solitary, those atoms begin to move again. A deer grazes, a caterpillar chews through green tissue with tiny jaws, a fish filters algae from water, a human lifts fruit to their mouth and bites, and in each case, the same thing happens. The atoms built by photosynthesis are transferred. This is the food chain. But seen not as a hierarchy of predators and prey, rather as an exchange network, an atomic economy. Life is not just energy flowing forward. It is matter circulating sideways, passed hand to hand, body to body, generation to generation. When an animal eats a plant, it takes in carbohydrates, fats, proteins, all built from atoms that were recently in the air. The animal breaks those molecules down, rearranges them, and rebuilds them into its own tissues. Carbon becomes muscle fiber, nitrogen becomes enzymes, calcium becomes bone, hydrogen and oxygen become water inside cells. The animal is not creating matter from nothing. It is borrowing matter from the world, reshaping it for a time, and then releasing it. Because animals also breathe, they also exhale carbon dioxide, they also shed cells, lose hair, drop feathers, leave waste. Their bodies leak matter back into the environment in 1,000 subtle ways. And when an organism dies, the exchange becomes even more complete. Decomposers, bacteria, fungi, insects, take over, dismantling the structures of the body and returning its atoms to soil and air. Over time, atoms do not stay loyal to any one creature.
The carbon in a wolf's heart may once have been in a pine tree, and before that in plankton, and before that in a cloud of gas drifting above the ocean. The calcium in your teeth may once have been part of a seashell. The nitrogen in your DNA may have traveled through countless living forms, through soil and sky, through roots and rivers. And this constant recycling is not a sign of life's fragility, it is a sign of its continuity. Life persists because it does not demand new matter each time. It works with what exists. It rearranges. It circulates. It remembers patterns, not atoms. Even the boundary of an individual body is not truly a boundary in the chemical sense. It is more like a temporary shoreline, where the ocean of the environment meets the shape of a person for a while, and then moves on. And at the center of this exchange, steady and rhythmic, is breath. Breath is the most immediate way the atmosphere enters you. Not metaphorically, literally. With each inhale, air travels down your throat and into branching tubes, narrower and narrower, until it reaches millions of tiny sacs called alveoli. These delicate structures are where the real exchange happens. Their walls are impossibly thin, designed for diffusion. On one side is the air you have drawn in. On the other side is blood, flowing through capillaries so narrow that red blood cells pass single file. Oxygen molecules, O2, drift across that membrane, not because they are pushed, not because they are pulled, simply because nature favors balance, and diffusion carries them from where they are abundant to where they are scarce. They dissolve into the fluid lining the alveoli, cross into the blood, and meet the waiting hemoglobin inside red blood cells. At the same time, Carbon dioxide moves in the opposite direction. It leaves your blood and enters the alveoli to be carried out on your exhale. Each breath is a trade. Oxygen in, carbon dioxide out. A quiet swap between your inner chemistry and the planet's open sky. But what happens to the oxygen once it enters you is even more intimate. Blood carries oxygen through arteries into tissues, down to the smallest capillaries. There, oxygen is released and diffuses into cells. And inside cells, in tiny structures called mitochondria, oxygen becomes part of a controlled burn, combustion slowed down and domesticated into metabolism. Your mitochondria take molecules derived from food, often glucose, born from photosynthesis, and they strip electrons from those molecules through a chain of reactions. It is an elegant process, one that captures energy in usable forms rather than losing it all as heat at once. And at the end of that chain, oxygen waits. Oxygen is the final electron acceptor. It receives electrons and combines with hydrogen ions to form water. This may sound simple, but it is one of the central pillars of complex life. Oxygen is chemical hunger. Its willingness to bind is what makes it so powerful in metabolism. It allows organisms to extract far more energy from food than they could without it. It supports movement, warmth, thought. It supports the electrical activity of your brain as it drifts towards sleep. And yet, even as oxygen powers your cells, it does not belong to you. It is passing through. You inhale it, you use it, and it becomes something else. Water, carbon dioxide, oxidized compounds, released back into the world. The oxygen atoms you breathe tonight will not remain in your body forever. Many will leave quickly. Some may stay longer, incorporated into molecules, joining tissue for a time. But eventually, they too will travel onward. And those oxygen atoms have a deep history. Oxygen is not made in large amounts by ordinary stars during their calm, long lives. Much of the oxygen in the universe is forged in massive stars, stars that live fast and die young. In their late stages, they fuse lighter elements into heavier ones, building oxygen in their hot interiors. And when they can no longer hold themselves up, when gravity wins, their cores collapse, and the star explodes as a supernova. In that explosion, oxygen is hurled outward at incredible speeds, thrown into space along with other elements. Shockwaves compress interstellar clouds. New stars and planets are seeded. The oxygen that fills Earth's oceans and air, the oxygen that binds to carbon in your exhale, the oxygen that accepts electrons in your mitochondria, was once inside a star that ended in fire. So every breath is not only a biological act, it is a cosmic inheritance drawn into your lungs in the dark, used to spark quiet energy in your cells, and released back into the night air. And oxygen does not travel alone. It rides in your blood with the help of another cosmic element, iron. If you could hold a single red blood cell in your mind, you might imagine it as a tiny boat drifting through a river of plasma. Inside it are hundreds of millions of hemoglobin molecules, each one folded into a precise shape. Hemoglobin is a protein built from amino acids, and at its center are special structures called heme groups. And at the heart of each heme group sits an iron atom. Iron is the reason your blood can carry oxygen efficiently. Without it, oxygen would dissolve only weakly in plasma, and it would be far harder to deliver enough to your tissues. Iron's electrons are arranged in a way that allows oxygen to bind reversibly, strong enough to pick it up in the lungs, but not so strong that it cannot release it in the tissues. This balance is exquisite. It is chemistry tuned to life's needs. When oxygen enters your blood, it binds to the iron in hemoglobin. The hemoglobin changes shape slightly, becoming more eager to bind additional oxygen molecules, until it is loaded. Then, as blood reaches tissues where oxygen is needed, conditions shift. Carbon dioxide levels, acidity, temperature, and hemoglobin loosens its grip. Oxygen is released. Cells receive it. Metabolism continues. Energy flows. This is your internal atmosphere, carried in liquid form, a moving sky inside your veins. And iron, too, has a deep and dramatic origin. Iron is not a common product of gentle stellar fusion in the way that carbon and oxygen are. Iron sits at a kind of turning point in nuclear physics. Fusing elements lighter than iron releases energy, but fusing iron into heavier elements consumes energy. That means that when a massive star builds an iron core, it is approaching the end of what fusion can provide. The star's internal engine begins to fail. Pressure drops, gravity tightens its grip, and then collapse. In the final moments of a massive star's life, temperatures and pressures become extreme. The core implodes, and then rebounds in a catastrophic explosion. In that violence, iron is created and scattered, some formed during the explosion itself, as atoms are crushed and rearranged in a flood of particles and energy. So the iron in your blood, the iron that makes oxygen transport possible, is the remnant of a star's death. A supernova's gift, cooled and collected over billions of years, incorporated into Earth's crust, dissolved into ancient seas, taken up by living things, passed through food chains, and finally embedded in the machinery of your body. It is almost too poetic, and yet it is simply true. Your ability to breathe efficiently depends on the ashes of exploded stars. And when you place these pieces together, the oxygen from supernovae, the carbon from stellar furnaces, the sunlight from fusion, the photosynthesis that builds food, the metabolism that releases energy, you begin to see a single continuous story, not separate chapters, not different worlds, but one long process, cosmic matter becoming planetary chemistry, becoming biology, becoming you. And still the story does not settle, because your body is not a museum of atoms, carefully preserved behind glass. It is a river. Even as you rest, even as you lie still, you are exchanging matter with the world. You exhale carbon dioxide and water vapor. You inhale oxygen and trace gases. You drink water and release it again. Cells die and are replaced. Proteins are broken down and rebuilt. Minerals shift between bone and blood. The lining of your gut renews itself with astonishing speed. The outer layers of your skin slowly shed, becoming dust that drifts away on air currents. Some parts of you are replaced quickly. The cells of your intestinal lining may renew in days. Many blood cells are replaced in months. Even much of the fat and protein in your body is in constant turnover. Molecules disassembled and reconstructed, as your metabolism responds to the rhythm of living. Other parts are slower. Some neurons may last a lifetime. Tooth enamel, once formed, hardly renews at all. But even then, the atoms within you are not frozen in time. They are part of chemical networks that interact with the environment, influenced by what you breathe, what you eat, what you drink, what you touch. Over years, a large fraction of the atoms in your body will be replaced. Not necessarily all at once, not in a dramatic sweep, but gradually, quietly, without announcement. The you that exists today is built from matter that has been cycling through Earth's systems for eons, and much of that matter will move on, continuing its journey through other forms. This is not a reason for unease. In the calm light of science, it can be strangely comforting. Because it means you are not isolated, or are not separate from the world you live on. You are participating in it, atom by atom, breath by breath. The boundary between your body and the atmosphere is crossed thousands of times each day. The boundary between your body and the biosphere is crossed with every meal. The boundary between your body and the ocean, the soil, the forests, the ancient stars, is thinner than it seems. You are, in a literal sense, a living collection of stardust, but not a static collection. You are stardust in motion. Carbon atoms that once drifted between stars now circulate in your bloodstream. Oxygen atoms forged in a supernova now wait at the end of your mitochondrial electron chains. Iron atoms from stellar catastrophe now sit at the center of hemoglobin, making your quiet breathing possible. And when you exhale, when you sweat, when you shed cells, when you simply exist through time, you return atoms to the world, and the world returns atoms to you. Earth's living systems are not just a web of organisms. They are pathways for matter to move. They are the planet's way of stirring its ingredients, of keeping chemistry active, of making the surface of a rocky world into something that changes and remembers and transforms. And if you listen closely, in the hush between breaths, you can almost sense that you are not only breathing air, you are breathing the long aftermath of stars. And when we step back from this quiet journey of atoms, a deeper realization slowly begins to emerge. That deeper realization is this: the atoms inside you are not simply travelers moving from one place to another. They are participants in a much larger rhythm, unfolding across entire galaxies, across billions of years.
a rhythm so steady and so patient that it can be easy to miss. And yet, it is always there, quietly shaping what the universe is able to become. If you could watch a galaxy the way you might watch a campfire, not in seconds but in ages, you would see it change its character, not just in its shape or its brightness, but in its chemistry. The galaxy would slowly learn new elements, like a language gaining new words. And with each new generation of stars, that vocabulary would expand. In the early universe, there were fewer options. After the first stars ignited, space was still simple in composition. Vast clouds were dominated by hydrogen and helium, with only traces of anything heavier. The earliest galaxies were, in a sense, chemically young. They could shine brilliantly, and they could form stars at astonishing rates, but the ingredients were limited. There was not yet an abundance of carbon to build complex molecules in cold clouds, not yet enough oxygen to make water common, not enough silicon, magnesium, iron, and all the other heavier elements that later became the foundation of rocky planets, metal cores, and the intricate chemistry of life. Those early stars lived fast, in a universe that was still learning what matter could do. Many of them were enormous, burning their fuel quickly, and ending their lives in violent deaths that flung new elements outward. Each death was not just an ending, but a chemical gift. The galaxy received those ashes and mixed them into its thin, restless gas. Over time, this gradual enrichment becomes one of the most important stories in astronomy: galactic chemical evolution. It's a phrase that sounds technical, almost dry, but it describes something deeply poetic. It means that a galaxy is not static. It is a system that changes what it is made of. It becomes more complex, more layered, more capable of building intricate structures. A later generation of star systems does not form from pristine material. It forms from gas that has been processed, gas that has been warmed, compressed, enriched, and stirred. The next stars inherit what the previous stars created. They are born already carrying traces of earlier lives, a little more carbon, a little more oxygen, a little more iron, and because of that, their planets, if they form, can be different too. In a young galaxy, rocky worlds are harder to build because the raw materials are scarce. In an older, enriched galaxy, those same worlds become more likely. Not guaranteed, but possible in a way that wasn't available before. So when you look up at the Milky Way, imagine it not only as a spiral of stars, but as a chemical history book. Every region has its own story. The inner parts of the galaxy, where star formation has been intense for a long time, tend to be richer in heavy elements. The outer regions, quieter and thinner, often hold a simpler mix. Even the oldest stars in the galactic halo carry clues, low metallicity, astronomers call it, meaning they formed before the galaxy had been heavily enriched. They are like fossils made of light, quietly telling us that there was a time when the cosmic pantry was almost empty. And yet, the galaxy kept cooking, because stars do not simply appear and remain forever. They are born, they live, they change, and they return what they are made of back to space. A star begins as a cold drift of gas and dust, barely noticeable against the dark. Then gravity gathers it, slowly at first, like a careful hand pulling threads together. The cloud collapses into a denser knot, temperature rises, pressure rises, and in time, at the core, something extraordinary happens. Fusion begins. For much of a star's life, it is a kind of steady engine. It takes the simplest element, hydrogen, and fuses it into helium, releasing light and heat. That energy pushes outward, balancing gravity's inward pull. For millions, billions of years, the star holds this quiet tension, gravity trying to compress, fusion trying to expand. The star shines because it is in a constant negotiation with itself. But stars are not all the same, and their endings are not all the same. Smaller stars, like red dwarfs, can burn so slowly that they outlast most of the universe's current age. Some, like stars, live longer than human history can easily grasp, then swell into red giants, shedding their outer layers into space. Massive stars live dramatically shorter lives, racing through their fuel, building heavier and heavier elements in layered shells, helium into carbon, carbon into oxygen, oxygen into neon, neon into magnesium, until the core becomes iron, a dead end for energy-producing fusion. And then, for those massive stars,
the story turns sudden. When the core can no longer support itself, gravity wins in an instant. The collapse triggers a supernova, one of the most powerful events in nature. In that moment, elements are forged that could not be made in steady stellar burning. Many of the heavier elements, created in the violence, in the rush of neutrons, in the brief, extreme conditions that only such an explosion can provide. But the point is not only the spectacle, the point is what happens afterward. Stellar winds, those steady flows of particles streaming from a star's surface, carry matter outward over long periods of time. Red giants exhale their atmospheres into space, leaving behind glowing planetary nebulae, delicate shells of gas that drift away and blend into the interstellar medium. Supernova, far more forceful, blast their contents outward at thousands of kilometers per second, sending shockwaves through surrounding clouds, compressing them, stirring them, and seeding them with fresh elements. This is redistribution. This is mixing. This is the galaxy constantly moving its material from one form to another, from one location to another. Nothing stays neatly in place. The matter of a star does not remain locked inside it forever. It returns to the wider environment, altered. And that is why the phrase cosmic recycling isn't just metaphor. It is a literal description of how galaxies remain fertile. The interstellar medium is not simply leftover gas waiting to become stars. It is a living reservoir, enriched by the past, changed by radiation, shaped by magnetic fields, stirred by explosions, cooled by molecules, warmed by starlight. It is the galaxy's bloodstream, carrying ingredients from old stars to new ones. In this way, the Milky Way is less like a collection of isolated suns and more like a single sprawling ecosystem. Stars are born from the galaxy, and then they feed the galaxy back. Birth, life, return, over and over, patient and persistent. And the cycle does not end with us. In cold, dark clouds scattered through the spiral arms, future stars are forming. They are gathering themselves from material that has been enriched by countless earlier generations. The gas is no longer the simple hydrogen-helium mixture of the early universe. It carries carbon that can form organic molecules, oxygen that can become water, nitrogen that can join in the chemistry of atmospheres and amino acids, silicon and iron that can build rocky planets and metallic cores, phosphorus, sulfur, small in abundance but enormous in biological importance. When these future stars ignite, they will be born into a richer universe than the first stars ever knew. Their protoplanetary disks, those swirling dusty rings where planets take shape, will have a more complex inventory, more solids, more compounds, more possibilities. And somewhere, perhaps in some future corner of the galaxy, on a planet that does not yet exist, chemistry may cross a threshold. Molecules might learn to copy themselves. Membranes might form. Energy might begin to flow through organized pathways. A quiet, persistent evolution might start to sculpt complexity out of the available atoms. Not because the universe aims for life, but because the universe keeps offering new conditions. It keeps building new environments. And when you have enough time, cosmic time, and enough experiments, planetary surfaces, ocean floors, atmospheric skies, then rare outcomes can happen. It's a strange comfort, in a way, to realize that the galaxy is still in the middle of its story. The matter that makes you up is not a final product. It is part of an ongoing process. Future worlds may be built from the same recycled elements that once passed through ancient stars, that later became dust, that later became planets, that later became living tissue, that later returned to space again. The atoms do not retire. They do not stop. They simply move from chapter to chapter. And that brings us to something quietly staggering. Many of the atoms in your body are older than the sun. The sun formed about 4.6 billion years ago from a cloud that collapsed and ignited. But that cloud was not new. It was already enriched. It already contained elements that had been made in other stars, stars that lived and died before our solar system existed. When the solar nebula formed, it gathered together this ancient material, gas and dust that had been drifting through the Milky Way for a long time. We know this not only through storytelling, but through evidence. Isotopes, different forms of the same element with different numbers of neutrons, act like timestamps and fingerprints. Some isotopes are stable, lasting essentially forever. Others are radioactive, decaying at known rates. By measuring isotopic ratios in meteorites, in ancient rocks, in tiny mineral grains,
scientists can reconstruct parts of the solar system's earliest history. And then there are the pre-solar grains. These are microscopic grains found inside certain meteorites, tiny crystals of silicon carbide, graphite, and other minerals that formed around ancient stars before the sun was born. They survived the solar system's formation, protected inside rock, and they carry isotopic patterns that do not match anything formed here. Their ratios of carbon isotopes, nitrogen isotopes, oxygen isotopes, strange, unmistakable signatures, point to specific stellar origins, red giant winds, supernova ejecta, perhaps even more exotic sites. They are, in a literal sense, stardust older than our world. And while not every atom in your body can be traced so directly, the principle remains. The material in you is a blend of ages. Some of it was forged in the first few billion years after the Big Bang. Some of it was shaped later, in the life cycles of stars that came and went before our sun ever lit up. Some of it may have drifted through interstellar space for immense spans of time, passing through clouds, warmed by radiation, cooled in darkness, perhaps incorporated into multiple systems before finally arriving here. Deep time is embedded in ordinary matter. The calcium in your bones, the iron in your blood, the oxygen you pull into your lungs, these are not fresh creations. They are old, seasoned by cosmic history. And when you sit quietly and feel your breath moving in and out, you are not just experiencing a biological rhythm, you are touching an ancient inventory of atoms, a collection that has been rearranged countless times, that has belonged to countless environments, that has waited through eras longer than any living mind can easily hold. And still, through all this change, something remains steady. Atoms persist, even as structures transform. A star can be born, shine, and die. A planet can form, cool, and crack into continents. Life can arise, evolve, and vanish. Civilizations can appear like brief sparks on a long night. Yet the atoms themselves are astonishingly durable. They don't wear out from being part of a mountain, or a sea, or a lung. They don't get tired from cycling through ice and vapor and blood and cloud. They simply move, rearrange, combine, separate, recombine again. In the everyday world, we learn a simple law. It changes form, but it is not created from nothing, and it does not disappear into nothing. In modern physics, we refine that idea. Mass and energy are linked, interchangeable under certain conditions. But for the chemical world of atoms, the continuity is still a powerful truth. The atoms in a breath out are the same atoms that will be somewhere else later. The atoms in a fallen leaf become soil, become gas, become part of another living thing. The atoms in a star become atoms in a nebula, become atoms in a new star, become atoms in a planet. Even across cosmic processes, this conservation gives the universe a kind of quiet coherence. The cosmos is not constantly throwing away its building blocks and starting over. It is working with what it has. It is remixing. It is reusing. And this endurance of atomic building blocks is part of what makes the universe feel, in a subtle way, intimate. Because it means that distance is not separation in an absolute sense. The same kinds of atoms found in distant nebulae are the ones in your hands. The same elements measured in the atmosphere of a far-off exoplanet are the ones your own body understands, because your body is made of them. In that sense, the universe is not a place filled with completely foreign substances. It is a place filled with familiar pieces arranged in unfamiliar ways. And if you widen your view just a little more, the whole picture begins to look like a system that wastes almost nothing. A universe that reuses everything. Stars are born from clouds enriched by earlier stars. They shine, they transform their interiors, they push matter outward through winds, and sometimes they explode, scattering elements across vast distances. Those elements drift, mix, cool, and gather again. New clouds form, new stars ignite, new disks spin into planets, new environments appear. Galaxies act as enormous recycling systems, not because they choose to, but because gravity and physics make it inevitable. A galaxy is a long-lived container. It holds on to much of its gas. It stirs it with rotation. It compresses it with spiral arms. It heats it with radiation. It seeds it with metals from stellar deaths. It is not a closed box. Some material escapes, some enters, some is blown out in galactic winds, but it is stable enough to maintain a continuing cycle, and over billions of years, that cycle becomes something like an evolving chemical ecosystem. Not a biological ecosystem, of course,
but a chemical one. A system where the species are elements and molecules, and the food web is energy and radiation and shockwaves, and the seasons are epochs of star formation and quiet intervals between. In some eras, galaxies are frantic, birthing stars rapidly, enriching themselves quickly. In others, they calm down, forming stars more slowly, letting their gas settle. But the overall direction is clear. More generations mean more complexity. More history means richer chemistry. This is one reason the night sky is so deeply layered. When you look at stars, you are not only seeing points of light, you are seeing stages in a long chemical story. Some stars are young, still wrapped in leftover disks. Some are mature, stable, calmly fusing hydrogen. Some are old giants, swelling and shedding. Some are remnants, white dwarfs cooling in silence, neutron stars spinning with fierce precision, black holes hidden but influential. And between them all, in the spaces that seem empty, the galaxy holds its raw material. Thin gas, faint dust, delicate molecules. The invisible supply chain of the cosmos. If you could listen to this cycle, if it had a sound, it might not be a roar. It might be more like a slow tide, a rise and fall, a gentle returning. Because the timescales are so vast that even the most violent events become, in the larger view, just pulses in a steady heartbeat. And you, here on one small planet, are part of that heartbeat. The atoms inside you are not on a one-way journey. They are in circulation, they came from somewhere, and they will go somewhere. The galaxy does not treat matter as disposable. It treats matter as reusable, endlessly rearrangeable, always eligible to become something new. And this perspective can soften the edges of time. It can make existence feel less like an isolated moment and more like a continuation. Not in a mystical sense, but in a physical one. A continuity written into the behavior of atoms, into the conservation of matter, into the long-lived cycles of star birth and star death. So when you think about your own body, about how it grows, changes, breathes, and eventually returns its material back to Earth, you can also remember that Earth itself is part of a larger exchange. Our planet trades atoms with space in subtle ways. Tiny particles drifting in, gases escaping out, impacts stirring old material, radiation shaping chemistry at the edge of the atmosphere. And beyond that, the solar system is part of a galactic environment that has been recycling matter since long before the sun existed. Everything is connected through reuse. The carbon in you may have once been in the atmosphere of a world that no longer exists. The oxygen may have drifted through a cold molecular cloud for millions of years before joining water on Earth. The iron may have been forged in a massive star that died before the sun was born, and then spent ages trapped inside a grain of dust, waiting to be swept into a forming planet. And if you let this thought settle in gently, without rushing, it begins to change how you see yourself in the story of the universe. Not as a separate thing dropped into an indifferent cosmos, but as a temporary arrangement of ancient materials. Materials with a deep past and a long future, a brief pattern, made possible by a galaxy that kept enriching itself, kept recycling itself, kept turning simple beginnings into complex possibilities. And once we understand this long cosmic cycle, we can begin to see our own existence in a new and quietly beautiful way. And that new way of seeing doesn't have to be dramatic or overwhelming. It can be gentle. It can be as simple as letting the idea rest in the back of your mind, like a warm, distant light. Because when you really follow the story to its quiet conclusion, you arrive at something both scientific and deeply personal. Not a metaphor, not a poetic exaggeration, but a literal truth written into the chemistry of your body. The atoms that make you were not invented here. They were not born on Earth. They were not waiting in a tidy container somewhere in space, labeled and prepared for life. They were earned, slowly, patiently, through a universe that had to learn how to make complexity. Your bones carry calcium that could only exist after generations of stars lived and died. Your blood carries iron forged under pressures so immense that even our imaginations struggle to hold them. The oxygen you use so effortlessly was once trapped inside a star's interior, where it was built atom by atom, like a quiet construction project running for millions of years. So when we return to that stardust idea, it changes its shape.
At first, it sounds like a comforting phrase, a bit of cosmic poetry. But then you remember the details. You remember that every element heavier than the simplest hydrogen and helium had to come from somewhere. That the universe began with a limited set of ingredients, and everything else had to be manufactured in the hearts of stars, or in the violent endings of stars, or in the collisions of dead stellar cores. And slowly, the phrase becomes less like poetry and more like personal identity. Not identity in the sense of a label, or a name, or a story you tell yourself, but identity in the simplest physical sense. What you are made of, what you are at the level beneath language. You are matter that has been rearranged into a living pattern, matter with a history that reaches back beyond your family, beyond your species, beyond your planet, matter that remembers in its own silent way an ancient universe. And if you let your mind drift backward along that timeline, it becomes almost impossible to find the true beginning of you. Not because you are vague or unreal, but because your components are so old and so widely traveled. Before there was Earth, there was the sun's protoplanetary disk, a rotating cloud of gas and dust, thick with recycled stardust. Before that, there were all the stars that had already finished their lives, sending out their enriched material. Before that, there were the first stars, forming from the simplest ingredients, lighting up a dark universe, and beginning the long work of transformation. And before even those first stars, there was a universe still young, still cooling, still learning what it could become. This is what it means to connect astrophysics with personal identity, but as a timeline that doesn't rush, a timeline that insists on patience. Because the universe did not create life quickly, it did not leap straight from the Big Bang to a world with oceans and forests and breathing creatures. It took billions of years just to make the right atoms in the right amounts, and then billions more for those atoms to gather into planets, and then into chemistry, and then into biology. And now, after all of that, those atoms are here. They are in you. They are doing something they have never done before in quite this way, at least not in this particular arrangement, on this particular world, at this particular moment in cosmic time. And as you sit with that thought, something even stranger begins to appear at the edge of the story. Because it isn't only that the universe made atoms, it's that the universe made a way for those atoms to notice. Somewhere along the long chain of cosmic events, matter began to wake up. Not suddenly, not with a flash of lightning and a dramatic announcement, but slowly, through complexity, through structures that could sense and respond, and then structures that could remember, and then structures that could imagine. Consciousness is still one of the deepest mysteries we have. We can trace the physical steps that lead to brains, and we can map the electrical activity that moves through neurons, and we can watch how chemicals shape moods and thoughts. But the inner experience, the feeling of being here, the quiet presence behind your eyes, remains difficult to pin down. And yet, whatever consciousness is, it seems to be something the universe can do. It seems to be a natural outcome of cosmic processes given enough time, enough energy, enough stable environments, and enough raw material. In other words, your awareness is not separate from the universe. It is not a visitor from outside physics. It is physics, arranged in an extraordinary way. Your thoughts are not floating above reality. They are part of reality. Your memories are not made of magic. They are made of matter and energy, organized into patterns that can persist. And that means there is a sense in which the universe is looking at itself through you. Not as a mystical claim, but as a simple consequence. The atoms inside your skull were once inside stars. Now they are part of a brain that can think about stars. The carbon in your neurons was once drifting as dust between solar systems. Now it helps form questions. It helps form wonder. The universe produced a creature that can measure the age of galaxies and then lie awake at night, quietly amazed that galaxies exist at all. This is one of the most profound implications of our cosmic origins. The universe is not only vast and ancient, it is also capable, in at least one small corner, of reflection, of observation, of curiosity. And when you consider that, the philosophical implications unfold gently, like a slow-opening flower in the dark. If the universe can become aware, then awareness is not an accident in the sense of being disconnected. It might still be rare, it might still be fragile, but it is woven into the same laws that govern stars and atoms and light.
You are not outside the story, you are a chapter of it, a way the cosmos experiences itself, a way it asks what it is, and that doesn't have to feel heavy, it can feel comforting, because the more you understand your connection to the larger whole, the more you can feel that you belong here. Not because the universe promised you anything, but because you are literally made of it. Belonging, in this cosmic sense, is not something you have to earn. It is not granted by approval or status. It is built into your existence. Every moment you spend on Earth is a moment spent in a universe that is still present inside you. The matter in your body is not separate from the matter in the stars. It is part of the same ongoing circulation. When you breathe in, you take in molecules that have been through countless journeys. Some of the oxygen you inhale may have been exhaled by forests, by plankton, by animals. Some of it may have been locked in ancient ice, or dissolved in oceans, or carried on winds across continents. And beyond Earth's cycles, there is the deeper truth that those atoms are part of a cosmic supply chain that stretches across time. The universe is not a collection of isolated things. It is a web of transformations. Stars form from clouds, planets form from disks, life forms from chemistry, thoughts form from neurons, and at every stage, the same matter is being repurposed. Interconnectedness isn't just a comforting idea. It is a physical fact. The atoms in your body were once part of other structures, other places, other eras, and one day they will be again. Not as a threat, not as a loss, just as a continuation, a return to circulation, a quiet recycling that has been happening for billions of years. So when you look up at the night sky, it isn't only that you are seeing distant objects. In a very real way, you are looking at relatives. You are looking at other gatherings of matter, other places where atoms are held in patterns for a time. And the distance between you and them is vast, but the connection is intimate. Because the same kinds of processes that shaped them shaped you. The same physics that makes a star shine drives the chemistry in your cells. The same electromagnetic forces that bind atoms in a nebula bind atoms in your skin. You remain physically connected to the cosmos, not by sentiment, but by law. And if you allow that to settle into you, it can soften something inside. It can turn existence from a lonely event into participation. You are participating in a story so large that no single mind can hold it all at once. A story written in galaxies and dust and time. A story that includes destruction and creation, collapse and ignition, death and renewal. And yet here you are, a living expression of that story, in a quiet room on a small planet. And now, gently let's bring that scale down. Let's take that immense cosmic history and place it inside something simple, a single breath. Because it's easy to talk about billions of years as if they are abstract, as if they are just numbers on a screen. But the truth is, those billions of years are present in the most ordinary moments of your life. They are present when you lift a glass of water, when you blink, when you rest your hand on your chest and feel it rise and fall. Think about what had to happen for you to exist as a breathing body. The universe had to expand and cool enough for atoms to form at all. Stars had to ignite and begin fusing elements. Some of those stars had to die, scattering the products of their fusion into space. New stars had to form from that enriched material. Planets had to assemble, and at least one of them had to be stable enough, and wet enough, and chemically fertile enough for life to begin. Life had to survive disasters. It had to endure ice ages, impacts, extinctions. It had to keep experimenting with forms and strategies. Cells had to learn to cooperate. Organisms had to learn to sense their environments. Nervous systems had to emerge, and eventually brains capable of forming a model of the world and a sense of self within it. All of that, just so that one day, on one ordinary night, you could inhale. And in that inhale, ancient atoms enter you again. Atoms older than mountains, older than oceans, older than the first animals, older than Earth itself. It's almost humorous in a quiet way, how easily we carry them, how casually we use them. The iron in your blood does not feel like a relic. It feels like energy, like warmth, like life. The calcium in your bones does not feel like the ashes of a star. It feels like structure, like support. The carbon in your cells does not feel like cosmic dust. It feels like you. And yet, that's exactly what it is. Cosmic history isn't only overhead. It's not only in the sky. It's in your everyday life, in your breath, in your heartbeat, in the simple fact that you are here and you can feel the passage of time. And maybe that's the quiet resolution we've been moving toward all along. Not an answer that closes the mystery, but a perspective that makes the mystery feel like home. Because when you take the long view, your life becomes both small and astonishing at once. Small, because you are a brief arrangement in an immense universe, a momentary pattern, a ripple, and astonishing because that pattern is real. It exists. It is happening right now, against all the emptiness and cold, against all the distances and timescales. There is a planet where matter has organized itself into a listener, into a thinker, into a being who can understand, at least a little, what the stars are doing. You don't need to force certainty onto this story. In fact, it might be more peaceful not to. Science is not a final proclamation. It is a method of listening, a way of asking careful questions and accepting honest answers, even when those answers are incomplete. There are things we still don't know. We don't know how common life is in the universe. We don't know how often consciousness emerges. We don't know whether minds like ours are rare sparks or scattered like seeds across the galaxy. We don't even fully understand our own minds. And yet, what we do know is already breathtaking. We know the approximate ages of stars. We know how elements are formed. We know that the atoms in your body were forged in environments far older than your world. We know that the universe has been building complexity for a very long time, and that you are part of that complexity. So instead of demanding certainty, you can let curiosity be enough. Curiosity is gentle. It doesn't need to shout. It doesn't need to win. It simply turns toward the unknown and says, "Tell me more." And in that spirit, scientific discovery becomes something almost intimate. A slow uncovering, a careful illumination, a way of seeing reality more clearly, not to strip it of wonder, but to deepen the wonder. Because a star is not less beautiful when you understand fusion. A galaxy is not less mysterious when you understand gravity. If anything, knowledge adds layers. It gives the night sky more depth, more texture, more meaning. It turns points of light into ancient engines, into nurseries, into graveyards, into laboratories where the universe experiments with matter. And it turns you into something equally astonishing. Not separate from nature, but an expression of it. Not a stranger in the cosmos, but a continuation of it. So now, in this final quiet reflection, I want to invite you to do something simple. Just pause for a moment and feel your breath. Not as a technique, not as a task, just as a gentle reminder that you are alive. As you inhale, consider that the air entering you is part of a story that began long before your first memory. As you exhale, consider that you are returning matter to the world, sending it outward again, letting it continue its journey. And as you rest in that rhythm, you might imagine the ancient stars that contributed to you. Not as specific named stars, not as a single dramatic explosion, but as generations, a long lineage of suns that lived, fused, and scattered their creations. You are connected to them, not by romance, but by continuity. The continuity of matter, the continuity of physics, the continuity of a universe that does not stop moving and changing, even when it seems still. And in that continuity, there is a strange kind of peace. Because even though individual lives are brief, the materials of life are enduring. They travel, they transform, they participate in new forms. The atoms that currently make up your body have been many things before. They have drifted through interstellar space. They have been locked in rock. They have been dissolved in water. They have been part of air and soil and sea. And now, for a while, they are part of you. A temporary gathering, given the rare gift of awareness. And one day they will move on, not as a tragedy, but as a return to the larger flow. A reminder that you are not isolated. You are not cut off. You are made of the same ancient substance as the stars, and you remain part of the same cosmic environment, even when the sky is hidden by daylight, even when you are indoors, even when you forget. The universe is not only around you, it is within you, and maybe that is enough for tonight. Not an answer to every question, but a soft place to rest your mind. Because if you ever feel small, you can remember that smallness is not the same as insignificance. A single breath contains chemistry that took billions of years to prepare. A single heartbeat is powered by elements forged in stellar cores. A single thought is carried by atoms older than the solar system. And as you breathe in again, gently, quietly, you can let that reality settle into you like a calm, steady gravity. Every breath you take is a meeting point between the present moment and deep time, between your life and the ancient universe, between the warmth of your body and the cold distances of space. And if you listen closely to the silence behind all this, you might sense the most comforting truth of all. You belong to the cosmos because the cosmos became you. And even now, in the vast darkness above us tonight, new stars are already beginning the slow process of creating the atoms of future lives.